Hello, my name is Mary Delellis, and I have been working with Alek Ivanovic and Julia James under Professor John Peponis to develop an automatic low-cost viscometer, which we call ViscoTech. Our goal was to design, test, and fabricate a device that can accurately measure the viscosity of various fluids ranging in temperature from 25 to 60 degrees Celsius, while keeping the cost to develop and run this device low compared to other currently used methods of measuring viscosity. To give a little bit of background on our device, viscosity is the magnitude of the internal friction between molecules of any given fluid. To put more simply, it can be described as a measure of how thick or thin a fluid is. Some important applications of viscosity include, but are not limited to, chemical engineering and adhesives, pharmaceutical applications, research in the food industry, and biomedical applications, specifically in bioprinting. Some of the constraints we were faced with in developing our device was that current methods of measuring viscosity are either very expensive or are difficult to make automatic. Newtonian shear thickening and shear thinning fluids are difficult to differentiate between while measuring viscosity. And the purpose of our particular project was to aid and to go along with the bioprinter, which we have at Lawrence Technological University. This printer operates in the temperature range of 25 degrees Celsius to 60 degrees Celsius.
Okay, so our device's design is really sort of based on this relationship between a fluid's flow rate and its viscosity. So that relationship is formally defined as the flow rate being inversely proportional to the viscosity of the fluid. But all that really means is that thicker fluids or more viscous fluids are more resistant to flow or displacement. So using that relationship, we can kind of infer another relationship that's similar between the velocity of an object traveling through some fluid and the viscosity of that fluid. And so that's the relationship that our device is trying to exploit in a way in order to indirectly measure viscosity. And then as far as the actual components that make up our device design, it can be divided into about 4 different sections. Number 1 would be the Lazy Susan. So if you take a look at figure 4C, that is the Lazy Susan section of our device. It's really just a large gear with a bunch of different sections or slots for different components. So there's the Arduino Uno controller board that's on top, as well as the breadboard. The hollow slot is for the paddle, and then the circular slot directly next to that is for our pressure sensor. And then underneath the Lazy Susan, which is actually the reason we call it the Lazy Susan, we've incorporated a fidget spinner to take advantage of the ball bearings to allow for a smoother rotational motion. And then there's the sample holder. There's not really much to explain there. It's just a specially designed container that's compatible with the rest of our design. The motor, we're using a Arduino stepper motor to drive the motion of the system. We considered using a DC motor for a little bit, but we didn't feel we'd have enough control over the actual velocity, so we stuck with the stepper motor. And then finally, there's the actual paddle. The bottom piece is being dragged through the fluid as the device spins. And then the intermolecular forces within the fluid that are opposing the paddle's motion create a reaction force at the top of the paddle between the paddle itself and the pressure sensor. And that's how we're actually measuring that force and then calibrating it to known viscosity values. And then lastly, how that force is actually being measured. We're using a simple voltage divider circuit. We've got a variable resistor, which is our pressure sensor in R1's position, and then a known resistor in R2, and then our known constant voltage source. And then we're just measuring the voltage in between the 2 resistors and then mathematically solving for a change in resistance.
So when we got to testing, we tested with known viscosities. We tested with water, olive oil, maple syrup, and honey. The first line of the table below shows literature research viscosities, and the numbers under that of the change in resistance is what we got from our pressure sensor and our device. When we graphed this, we came up with an exponential relationship shown in the figure 6 underneath the table. The exponential fit is not what we're looking for in a, we're looking for a linear correlation, but this will be fine as long as the test results are repeatable. The current challenges we have right now is that the pressure sensor is not as sensitive as we would like it to be, so that we can test test smaller increments of viscosity. We also can't really differentiate between Newtonian shear thickening and shear thinning fluids due to the simplicity of our design. We also found that the material that we're using for the solution holder is too porous to be used at the moment, so we have to work a little bit more on our device design in order to fix that issue.
And then in conclusion, so an automatic low-cost viscometer prototype was fabricated and tested. Our preliminary results show a good exponential relationship between viscosity and the device's measured values. But like we said before, we will need to do a little more testing in order to validate the exponential model. And then most importantly, the theory driving our design has proven to work for this particular device, as well as other methods that we sort of tried to mirror with our design. And then further testing will need to incorporate a temperature sensor to better align with the bioprinting applications. The graph over on the right, figure 7, that's just kind of showing just the relationship we'd expect to see as temperature increases. We'd expect to see a decrease in viscosity. And then obviously we'll need to test the bioprinting gels without the use rheometer in order to determine specific viscosity values at specific temperatures, and then recalibrate our device using those values.
We would like to thank Lawrence Technological University for the use of their laboratories and equipment, as well as our advisor, Professor John Peponis, for his guidance in completing this project.